now let's look at the proof, which will give us a lot of intuition. Okay. So in this proof, I'll introduce to you one of the oldest tricks in the book, in the math book, which is proof by contradiction. Okay. There are various other proofs possible, but we are going to go by contradiction. Okay. So the intuition behind it is going to be the following before we go to contradiction. So I'm going to write down the first order theorem which we will use, right. This is the first order theorem, right, and what are we trying to investigate? Whether or not x star is a minima of the function, right. What does this remind you of? We did this in the previous class. This looks like a directional derivative, like rate of change of the function in the direction p, right. That is what is the meaning of this guy. Now if x star is going to be a minima, then the rate of change of the function in any direction away from this point should be what? Positive. The function should always increase as I go away from this point. There should be no direction in which the rate of change is negative. That means there exists a lower point if I were to find such a direction, right. So it's basically, if you look back at this cone and this bowl over here, the rate of change of the function, no matter what direction you look, it's always increasing if I were at a true minima. On the other hand, if I was sitting over here, there is one direction in which the rate of change is taking me to a lower point, right. So that is the kind of intuition you can keep in mind as we go to the proof. It will become clear now. Okay. So let's start. Yeah, in a direction. At x is of course 0, but notice this is grad f at x star plus tp, right, not at x star. Grad f of x star should be 0. So what is the contradiction that we'll assume? Which says that assume x star is a minimizer, but grad of f at this point is not 0. So this is the contradiction that we are going to assume. Okay, so let's go step by step to see what soup this contradiction lands us in. Okay, it's always easier to work with scalar functions. So I'm going to cook up a scalar function, and the hint or the intuition for that scalar function actually is coming from this first term sitting over here. That's why I gave you the intuition first. So I'm going to call g of t. T is a scalar, remember, from 0 to 1. So g of t I'm going to define to be precisely this term. I'll just take the transpose the other way. Fine. Now I'm going to try to see if what good this does us. Okay. So now p is left unspecified. I have not said anything about p. P can be any point that I want. So it's up to me to choose this p, right. So we can choose any p, right. Supposing I choose p to be the negative gradient of f at x star. So what happens to my g of t? It simply becomes grad f of x star transpose grad f of x star plus tp, right, which doesn't look that interesting. You might look at it and say so what, but let's see what happens. What is g of 0? Minus norm of grad f x star squared. Now this is something that I can say something about. What can I say about this? Is it weakly or strictly? Strictly less than 0, because I have assumed that grad f star is not 0. So this is strictly less than 0. Okay. Now because of what I had assumed about the function being continuously differentiable, right? So here is the catch over here. Let's note that down as step 3. GT is a continuous function, right? Therefore, if I were to make a graph of g of t, okay, simple graph like this. This is t, g of t. At what point should I mark g of 0? Above the origin, below the origin? G of 0 is strictly negative. So g of 0 must be some point over here. Has to be, right? Further, g of t is a continuous function. That means that it will be something like this, let's say, or any shape. Point is that it cannot jump to plus infinity in a delta tending to 0 distance, right? That's the meaning that it is continuous, right? So it implies that g of t is still less than 0 for some small t. I can always find a small enough t such that g of t is less than 0, right? So now we are beginning to tighten the noose. Now what is g of t? We have already written it over here. This is my g of t. Okay. Now, as the phrase goes, our goose is almost cooked. Let's go back to our statement of the first order theorem. I had right. That was the statement of the first order theorem, right? This is exactly what. Doesn't this look like g of t? It looks like g of t. P is not specified, so I specify some p to be minus grad f. So this is essentially nothing but g of t, right? And this g of t, as I have shown you over here by simple logic, is less than 0, right? Do you see the contradiction now? Right. So do you see the contradiction now? I have f of x star plus a negative quantity is equal to f of x at some other point. What does that imply? Implies that now I have got f of, there is some point given by this t and p which is less than f of x star, strictly. Its function value is lesser, it's f of x star minus something, therefore it is lower, right? So this contradicts our original statement which said that assume x is a minimizer. Therefore, I have found a new point which is given by x star plus tp, which has a lower function value. That means x star was not a minimizer, right? So this would imply that x star plus tp is a better minimizer, let us say. Or you can say that x star is not a minimizer. Let's scratch that line, that's not very rigorous. It just implies that x star is not a minimizer, right? So that's the contradiction. Yeah. Gradient, exactly, which is why I needed it in the theorem statement. Correct, exactly, right? So you see that every part of a theorem statement gets used later. Without it, you could not have done it, right? If it was just that it exists, but is not continuous, then I cannot make this argument. Then the gradient can suddenly jump, like in the case of the king, right? That's why continuously differentiable is needed. Very good. Okay, so right. So this is your first order theorem. I'm not going to prove the second order theorem. It's there in Nossertle and Wright if you want to have a look. It's a little lengthy, so we won't do it. Okay. So this is how the simplest test to search for a local minima is find its gradient and set it equal to and check whether or not it's equal to 0, which is a necessary condition. This is not sufficient. For sufficiency, we have to go to second order conditions.